Welcome to the fascinating world of neuroscience. Today, we are going to explore sleep neurophysiology. You might think of sleep as a simple time of rest, but as we will soon discover, it is one of the most active, complex, and critical processes your brain undertakes. Let us dive in and uncover what really happens when we close our eyes. To start our journey, imagine a bustling, chaotic city during the day. When night falls, the city does not just shut down. Instead, a completely different crew takes over. Street sweepers clean up, and filing clerks organize the day's paperwork. Your brain operates in the exact same way. Sleep is not a passive state, like unplugging a computer. It is a highly active, incredibly busy period where your brain is hard at work, cleaning out toxic waste, repairing cellular damage, and organizing your memories. Without this dedicated night shift, the city of your mind would quickly collapse. Now that we understand the purpose of sleep intuitively, let us look at how neuroscientists formally define it. In neurophysiology, sleep is a naturally recurring, highly regulated state of mind and body. It is characterized by altered consciousness, relatively inhibited sensory activity, and reduced muscle activity. It is very important to note that unlike a coma or hibernation, sleep is rapidly reversible. This means a loud noise or a strong shake can quickly bring the brain back to full wakefulness. This rapid reversibility is a key hallmark of healthy sleep architecture. Building on that definition, neuroscientists divide sleep into two massive categories, starting with non-rapid eye movement, or NREM sleep. NREM sleep is further broken down into three distinct stages, known as N1, N2, and N3. As you move through these stages, you progress from light drowsiness all the way down into deep, restorative, slow-wave sleep. During these deeper stages, if we measure the brain's electrical activity using an electroencephalogram, we see a dramatic shift. The fast, chaotic waves of wakefulness transform into slow, synchronized, and powerful waves that facilitate physical healing. After progressing through NREM sleep, the brain enters the second major category, rapid eye movement, or REM sleep. This is often called a paradoxical state, and for a very good reason. During REM sleep, the brain's electrical activity looks almost exactly like it does when you are fully awake and alert. However, to protect you, your voluntary muscles are completely paralyzed. This temporary paralysis prevents you from physically acting out your dreams. This highly active brain state, combined with an immobilized body, is why REM sleep is so unique and critical for our mental health. Having explored the stages of sleep, we must ask, why is this architecture so vital? Sleep occupies nearly 1/3 of our entire lives, and chronic deprivation leads to severe cognitive decline, emotional instability, and a weakened immune system. Perhaps most fascinating is what happens during deep NREM sleep. The brain's glymphatic system physically opens up to wash away amyloid beta proteins, which are the exact toxins associated with Alzheimer's disease. Furthermore, without this structured sleep, our brains would fail to consolidate short-term learning into long-term memory, making education and skill acquisition virtually impossible. Understanding the biology is crucial, but clinicians also need objective data to diagnose disorders. This brings us to one of the most important clinical formulas in sleep medicine: sleep efficiency. The formula is SE equals TST divided by TIB, multiplied by 100. Here, SE stands for sleep efficiency, expressed as a percentage. TST is total sleep time, which is the actual number of minutes spent asleep. TIB is time in bed, the total minutes from turning off the lights to getting out of bed. If your total sleep time increases while time in bed stays the same, your efficiency goes up. If you lie awake tossing and turning, time in bed grows and your efficiency drops. Let us apply this formula to a real clinical scenario. A patient visits a clinic with severe insomnia. They went to bed at 10 p.m. and got out of bed at 6 a.m., which is exactly 8 hours. First, we convert this to minutes by multiplying 8 by 60, giving us a time in bed of 480 minutes. The sleep study reveals they were actually asleep for only 336 minutes. We plug these values into our formula, dividing 336 by 480, which gives 0.70. Multiplying by 100 gives a final sleep efficiency of 70%. Since a healthy adult should be at 85% or higher, this confirms a diagnosis of poor sleep continuity. Now that we have evaluated overall sleep quality, let us look at the internal architecture of a night's sleep. A healthy adult progresses through a complete sleep cycle, from light sleep to deep sleep and into REM, approximately every 90 minutes. To find the number of complete cycles a person experiences, we use the formula NC equals total sleep time divided by 90. Here, NC represents the total number of complete sleep cycles, and TST is the total sleep time measured in minutes. If a person sleeps longer, their total sleep time increases, which directly increases the number of restorative cycles their brain can complete. Let us see how this works for a university student who sleeps for exactly 7.5 hours before a major neuroscience exam. First, we need to convert the total sleep duration from hours into minutes, so our units match the 90-minute cycle. We multiply 7.5 hours by 60, giving us a total sleep time of 450 minutes. Next, we divide this 450 minutes by the 90-minute cycle length. The result is exactly 5. This means the student's brain successfully navigated the journey from light sleep to deep sleep and back up to REM 5 separate times during the night. Having calculated the number of cycles, we must also consider the composition of those cycles. REM sleep is absolutely vital for memory consolidation, and in a healthy adult, it makes up exactly 20% of the total sleep time. We can express this mathematically with the formula TR equals total sleep time multiplied by 0.20. In this equation, TR represents the total time spent in the REM stage, measured in minutes. As total sleep time increases, the absolute minutes spent in REM sleep also increases proportionally, giving the brain more time to lock in the information learned during the previous day. Let us continue with our university student who achieved a total sleep time of 450 minutes. We want to know exactly how much time their brain spent in the critical REM stage. We take the total sleep time of 450 minutes and multiply it by 0.20, which represents the 20% proportion. The calculation gives us 90 minutes. Practically, this means the student spent an hour and a half in the dream-heavy REM state. This is an excellent outcome, ensuring that their study material from the previous day is well consolidated and ready for their exam. To truly visualize everything we have discussed, let us look at a sleep hypnogram. This graph maps the progression of sleep stages over an 8-hour night. On the horizontal axis, we have time in hours, and on the vertical axis, we have the sleep stages, from awake at the top down to deep N3 sleep at the bottom. Notice the red band representing REM sleep. The black line traces the brain's journey, dipping down into deep sleep and rising back to REM roughly every 90 minutes. Observe how the dips into N3 deep sleep are longest during the first half of the night for physical repair. In contrast, the peaks into REM sleep become much longer in the second half of the night, prioritizing memory consolidation. We have covered a lot of ground today, so let us review the most important ideas. First, sleep is never a simple turning off of the brain. It is a highly dynamic neurophysiological process that cycles through distinct NREM and REM stages. Second, each stage serves a unique biological purpose, from physical cellular repair and toxin removal in deep NREM sleep to complex memory consolidation during REM sleep. Finally, by measuring metrics like sleep efficiency and tracking 90-minute cycles, neuroscientists can deeply understand brain health and diagnose disorders. You now understand the architecture of sleep and just how hard your brain works in the dark to ensure you function optimally in the light.